So why do we always just focus on least squares estimators? Why is that sort of what we always do? Well, under the assumptions of the classical linear regression model that I had up a few minutes ago, OLS, which stands for ordinary least squares, provides the minimum variance, in other words, the most efficient, unbiased estimator of beta naught and beta 1. It is also the maximum likelihood estimator under normality of errors, and the estimates are consistent and asymptotically normal, okay? And these things are not true of the other estimators. So that's why we typically always use the least squares estimators. Are there cases when you might want to use a least absolute deviations estimator? Maybe. I mean, maybe if you're particularly worried about the credibility of your data and you think you might have some outliers that you don't want to take out of your data set, but you don't want them to have undue influence on your parameter estimates, you might be able to justify using a least absolute deviations estimator. But typically, people are going to go for the least squares estimators because its properties are so good. Yeah, oh, sorry. Yeah, go ahead.
And so is the reason that OLS is favorable, is that like even though they're both based on the same distance, I guess, the sensitivity in the OLS is higher because it's just squared? Or?
Yeah, it's more sensitive to sort of observations that are kind of out in the tails because it's squared. But even given that, it still has all of these favorable properties. So, do you have a question?
I guess not really anymore. I was sort of thinking that the first characteristic is a little bit circular because we define efficiency in terms of variance, and so if you had another metric for efficiency, it wouldn't necessarily be. But I guess what you're really saying is that it provides the minimum variance.
Exactly. Yeah. So I just put in parentheses most efficient to just remind you that that's sort of how we defined. Yeah. That's the terminology we used, basically. But yeah. Yep.
These properties of OLS hold if homoscedasticity goes out the window, or?
So, good question. I would have to think for just a second. So, basically, that's no longer the most efficient. It's still unbiased. It's no longer the most efficient. The inference has to be, under heteroscedasticity. The sort of standard inference that we'll see over the next couple of lectures has to be modified because then the standard errors, if you use kind of the standard inference, are biased. But it's still going to have good properties, and we have very good ways of sort of fixing, of recapturing the best properties under the case of heteroscedasticity. Okay, so fine. Maybe, I hope I've convinced you that least squares estimators are the way to go and the way that we're typically going to estimate this linear model. So we've got, sort of all of these, like sum of squared, sort of residuals, and we're trying to choose the line that's sort of minimizing those. Does that mean we have to do a numerical minimization every time we want to solve for our least squares estimators? No, we don't. We have these lovely closed form solutions, okay? So all we have to do is plug into these formulas, and realistically speaking, all we have to do is type, like the command into R. So anyhow, if you sort of went on to do more advanced econometrics, you would in fact encounter estimators where you have to do complicated numerical minimizations every time to get parameter estimates. OLS is not one of them. We have these nice closed form solutions. Okay, how did I get these? Pages of tedious calculations that are up on the website for your viewing pleasure. The notation is slightly different. I believe in those notes, instead of having the intercept denoted by beta naught, I think I used an alpha instead, and then a beta for the slope. So I changed the notation is slightly different. But anyhow, you can look at those if you want. However, I don't want you to get the idea that OLS estimators are horrible, complicated things. They're really very elegant and they're very intuitive, but the thing that's holding us back is this notation. Okay? So actually next time we will derive the least squares estimators using matrix notation, and you will see how beautiful they are. I'm not going to drag you through the derivation using the summation notation because it's painful. And as I just said, they could be lovelier still if we weren't too afraid of using matrix notation, which we're not. So we'll do it next time.